it's a little bit like going to a cinema, watching Opus Suite and having some crackers. It's perfect. Anyway, I'll continue with just a demonstration. I will skip the PowerPoint slides here and just jump right into to Opus Suite and show you an addition to the model. I'm not going to build it up either. I'm just going to show you what it looks like. So what we've done here is that we have created a variant of our helicopter. So before we had our standard variant, but now we have something that we call a night variant. So this is a variant of the helicopter that is equipped with an additional subsystem, which is used to be able to operate during nighttime as well. So what we do is that we create another variant out of our product. So I start to show you just the product variant table. You see here, we've added the helicopter night variant. And this is the smart thing here, that a variant can be defined by another variant. So this means that sort of the parent of our night configuration has the standard variant as its parent. And that's why, if you look at to the left here in the model view, you can see that this night variant, it has the standard subsystem of the engine, which we modeled for the original variant. However, it is sort of a little bit grayed out. You see that the color, both of the nodes as well as the descriptions of the items and the breakdown elements, it's a bit faded. And that means that it's we use this again. Try to use color coding to explain what different things means. But the idea here is to show that those are inherited from the parent. So you see that the night variant has the parent helicopter variant. So it gets all the structure elements from the original variant, which you see here, but they are again a bit grayed out. And then, so I can collapse that one, but then it also has an additional subsystem, that is the enhanced vision system. And it consists of four elements with their corresponding items as well. So there's an infrared camera, there is some mechanics, a display, and some playback capability or recording capability. So recording device. So that's what it looks like. And then, of course, what we do is that we define how many of our operational systems is it that are according to these different configurations. And have this, if you remember, in the organization category and the operations category, and the system deployment table. We now define that we still have actually 6 and 3 of the original variant, but we also have 4 of the night vision variant at the alpha base. All right, and we've also added another type of mission. So we also have the helicopter mission at nighttime, as you see here, and obviously it's incorporated into the operational profile as well. So it's kind of easy to add another variant, as I said, because we can simply work with the inheritance. So it takes all the properties, everything, including the reliabilities and the maintenance and all of it. So we really don't have to do anything. We just add those 4 additional items and the information for them, of course. Right. Once we have this, there's one more thing I want to show you. We've actually added an extra operation parameter here. Do you remember that I said yesterday that we can define failures per operating hours? That's the number of failures or number of events per operating hours. That's sort of the standard way. But here is also an additional way to define user specific operation parameters. So here we added night operating hours, which is different from the standard operational hours. And we can add here in the mission type utilization. This is a little bit detailed, but it's just to show you that it's how it works and that it's possible. So we have this mission, the mission type, nighttime, and we use the helicopter at night, and then it's this night operation hour. So the utilization per system is 1 per hour. So it's a different operation parameter, and then we can also have failures in this one. So if you look, let's see if I can find the failure rate table. Hopefully there is, as you see here, we can define, there are, as you see, failure modes for those items in the vision system, subsystem here. You see that they are defined per night operating hours, not standard operating hours. So it means that what we want to achieve is we want to tell the model that those things are just, they are only in operation during night. Otherwise they're not, so they're not producing errors if you're flying in the daytime with those variants. So a detail of the model. One more thing on the input side here is to look at mission systems. And here we can define also, we remember that we had 2 different mission types. We have the standard mission and then we have the nighttime mission. But we don't want the model to take from the standard configuration of the helicopter and use that one for the nighttime, because that's not the reality. We cannot operate at nighttime with the standard configuration. So that's why we need to tell the model that for those missions, we can only operate with the night variant. And again, here we have also nominal number of systems 2 and the minimum number of systems to sort of see the mission as successful is only 1. Otherwise, it's all the same. Run the simulation. We run 100 replications here. Coming to the results. Hopefully, we're still at the system results, system unavailability. But so we can look at, I wanted to show you the mission results here to show you that it's how it differs between the 2 different type of missions. So here we're looking at system time for the mission. So how many system hours are we producing while on mission? And as you see, we are requesting much more. And this is accumulated, so it's a total over the 5 years. So we are requesting almost 40,000 hours for the daytime missions, and then approximately 20,000 hours in total over all the systems for the nighttime missions. However, as we see here, we do not achieve the same amount of hours here, right? And we can also view it in percentages, maybe. Oh, that's a little bit annoying. You see what happened there, that they switched place, but because they are alphabetically sorted, but I think if I do this, it's better. So here I can do sort by values. You see, this is the selection now. I can say that I want to sort the missions descending instead on alphabetically and whatever way I want to do it. So now this way I lock them to their locations. So if I do undo the results in percent, you see that it's not moving. So this is just small tips and tricks so that you don't get annoyed when you work with the results while they're moving sides. So if you see the result in percent, you see it's almost 30% of the system time that is not achieved with the nighttime. And then you wonder, well, why is that? And it's because, of course, it's because we have more items on the nighttime helicopters. We have an additional subsystem, so we have more components that can fail, more things that can fail. So the more complex the system becomes, often the tendency of failure increases as well. And that's important to understand also when you're modeling. You see this, that yeah, sure, we can go with the night vision, but it's not so reliable. So we get a lot of failures on it, and that's why we are losing quite a lot of the operational time, the planned operational time as well. So we only have a 70% success or system time accomplishment here compared to the 97% in the original case. No questions so far? Then I'll move on to one more. Yeah. This blog is now a little bit about uncertainties, and this is something that I personally think is pretty interesting and exciting, and data uncertainty. Over all my years at Systicon, I constantly meet people who says that, well, now I cannot do any analysis because we don't trust the data. It's uncertain. We don't know failure rates. No, we don't know. We don't know if it's 10 or 15, so we cannot do any modeling. Okay, and yeah. Okay. So that's the statement that I've met a lot of times. So to answer this, we want to remember some things. I think I showed this, or Oscar showed this graph actually the first day. If we look at how the costs are accumulated over the life cycle, x-axis here is the life cycle, all the different phases and so on. The important part is here, so when we commit to the costs, well, way earlier than they actually appears. So costs accumulates and appears at a later point in time, but decisions that we take already in the early phases will affect and will sort of lock down the costs in the early phases. And this means that our possibility to influence the future costs will decrease over time in the same manner. So the earlier we can start with modeling and analysis, the better influence we will have on the final life cycle production. Okay, so you remember this as well, that it's never too late to do things wrong. So it's important with modeling at any point in time, because the costs will arise and go very high if you do not know what decisions you're taking. So how can we work with the uncertainty of data? Well, if we are in the very early phases, we typically we don't know, right? So we have to work with some kind of estimates, engineering estimates or experience estimates from other similar systems and so on. But we can still do estimates, even though we have never flown with this helicopter or aircraft. We can still estimate, right? And that's a part of course, any system design team as well. They are also responsible for estimating things. We're doing FRACAS and other activities in the IDAS and IPS domain. If you're at a later point, maybe if we are an operator of a system, we buy this system from someone, so there's a manufacturer who actually we can contractually demand to get this kind of data. Otherwise, we're not buying the systems. And we see that more and more, that actually it's becoming quite common that the buyers are demanding data from the suppliers. Anyway, when we get into operations and so on of the systems, we can actually start gathering experienced field data, but that's kind of late. So people say that now we don't know, we don't have any experienced data. Well, there are ways to get data earlier as well, and Of course, the earlier we are, the uncertainty will be bigger, but we can't wait. If we wait until we are, now I know, perfect, now I have 10,000 flight hours of this engine system, so I know exactly what failures rates I can expect. But that's probably somewhere here, and there are not so many decisions to take here. So we have to do something. We have to start to take the decisions here, even though we say that the uncertainty is big. Okay, so how can we work with this? One example of an approach for estimating data for this kind of modeling and analysis that we are talking about is to use a matrix grouping of the components. So in this graph here, we see the y-axis as the price. For example, the price is an important input parameter for the spare part optimization, of course, but also failure rate. So those are two very common data that you maybe don't know in the early phases. So what do? Well, we create we divide those dimensions in different sections. So we say that we split up the failure rate. It can be either between 0 and 50, or 50 and 100, or between 100 and 500. Okay, same thing for prices. We split it up in sectors and say that each component can be either in the span between 0 and 10,000, or between 10 and 100, or 100 and 500,000. Something like that. It's an example. And then what you do is that you look at your components and then you estimate. And we say that I guess that this cost probably will be somewhere between 10 and 100,000. And it's kind of probable to fail as well, so we will box it here between 100 and 500 for the failure rate. Same thing for next item. This one is really expensive, but it's quite reliable, so it's probably in this first sector for failure rates, but it's expensive. And next, and next, and next, and we move on. We do this for all the items. So then we have sort of boxed our, whatever we have here, 30 items in this example. And that's a good start, but that's not all. And this is something that I've, together with some of my colleagues in Sweden, we've done some research on this lately because it's pretty, I think it's interesting and important. So what we did was that we said that, okay, we have this set of 30 items here, and we say that, well, we have boxed them in groups, and if we can do that, and then we can use random draws, sort of a simulation. We say that, okay, it can end up somewhere in this. We make a random draw saying that it's, for each item, it's between this value in price, it's between those two values in failure rate. So each item will end up somewhere in those boxes. Okay, and then we do that many times, like a simulation. We get a lot of outputs. And then we can, when we're doing support costs, skip that one. Yeah, you know, here we can compare alternative 1 to 2 with the estimated failure rates. And so this is what we do for all the outcomes of this sort of, that's if we do 500 replications. So we do 500 random draws. And this is an example of one of them. So we get two different, of two of them. So we get two different alternatives. Okay, sorry, I don't explain this well. When we want to perform a decision, we typically have two alternatives to decide between, like we did for that engine X and Y before. So that's what we're trying to do here. We have two alternatives, 1 and 2, or X and Y, okay? And they have different design, etc. And we have done this, what we did was that we did this random draw for both of the alternatives. So two different alternatives, and we do perform random draws for them. And one such outcome, one such replication, if you want to go for 95% availability here, we can see that the cost increase was quite high for one of those. And here's the thing: if we say that we are not sure about this data, so this single replication or this single estimation of the data, it's not enough. So what we did was, okay, we did 500 replications, and then we had this uncertainty of when we were boxing the failure rate and the prices. So we get, for alternative 1, this is 500 different Opus 10 runs. I didn't do them manually, if you wonder. we programmed it, but anyway. So we did 500 replications, and I drew these 500 lines. And then for the second alternative, we also did 500 replications, and with random numbers. And this is what we typically see, that the solutions from the optimization is quite robust. So the spread is not so big. So that means that even though we have quite high spread on the cost and failure rate, the result in terms of number of spare parts is quite robust. And it turns out that the two alternatives that we are selecting between, maybe two different system designs. So the first alternative is always better here. And that's, of course, this won't be true in 100% of the cases. In some cases, they will interfere. But it was surprisingly how tight those 500 different curves ends up to each other. And I think what I ultimately want to say with this is that the solutions from the spare parts optimization is quite reliable, even though the input data varies. So even though the failure rate goes up from 300 to 500, the resulting answer that we're looking for, which is the number of spare parts, is still 3. And if the failure rate drops to 25, well, the answer is still 3 in the number in stock size. So it doesn't have to be a big change in the result just because the input data is a little bit uncertain. And that's what we were trying to prove with this method. Okay. Some words on automatic data generation as well, which could be another approach on a very early phase analysis with OPUS Suite. Simple variant here of our product. We have 3. Let's say that we're in a conceptual phase of building a new system. And we think that our systems of ours is going to contain 3 different subsystems. We call them A, B, and C. Okay, and we know that we have to, because of the operations that we're going to do, we can estimate an availability of this variant that we are going to produce. Okay, let's say that we want to have 98% availability. That's the target for this product. Okay, and that means that if we split that evenly into 3 different subsystems, given that they are operating in series, we can calculate that we need 99.3% availability for each of those subsystems. Kind of simple mathematics. And if we also know that the mean time between failure is 240, so we don't want to have more failures than that. That's an estimation. We can split that up depending on what type of, if we can estimate the mean time to repair as well for those subsystems, we can calculate mean time between failures for them as well. Might differ a little bit. Maybe in this case we said that, well, here we assume that it takes 4 hours to repair. It takes 5 hours for this one and 6 hours for the last one. So that's why the mean time between failures will have to be these numbers in order to reach this targeted availability. And from a mean time between failure, we can of course calculate the failure rate. So that's straightforward. So what can we do now? Why did we do this? Well, then we can use something that is built into OPUS Suite, which is an automatic data generation, or item generation in this case. So there's a screenshot from OPUS Suite. So what we do is that, okay, we say that we have a product variant called variant here, and we want to create a parent that is the subsystem A, and we can give some prefixes for the breakdown elements and how many items do we think that it will consist of. We say 5 items here, for example. Yeah, we call them item A, and then we get the number as well. And what we do is that we say here that we give that failure rate, if you remember from previous slide, For subsystem A, it was 1,689. So we keep that total failure rate for this subsystem here, okay, and we say that it's 5 items, and then we press the OK button here, and of course we also gave a total price, which was another estimation. So what's the total price for the items in this subsystem? And what we automatically get from OPUS Suite is that it randomly draws numbers according to these numbers and creates both breakdown elements and items and realizations and the product breakdown, all that automatically according to those numbers here. So we get the item A1 to 5, the 5 items that we asked for. Here we get random numbers between 0 and 1,000, and here we have the total failure rate randomized, but still created from that original number that we had in the table. And then, of course, we can do the same thing for the other 2 subsystems, and all of a sudden, we have a pretty good start. Here we have a model that we can start working with. And the only thing we started from was a total availability and an assumption on the mean time between failure. And then we actually have a model. And here we can start now playing around with things like operational availabilities and all the other things that we're looking at. And this slide is not in the correct order, so it should be earlier. But it's just the question was here if it's highly accurate data requiring early phase decisions, and we, as I tried to prove, no, not necessarily. Okay. Yeah, I do some quick more slides too, and then we'll go back into the suite for some more examples before lunch. But so, what kind of variations over time can we do with SimBlocks? Well, so here's a typical question. We're about to phase in 5 new helicopters over the next 5 years. Okay, so how can we model that? It's not that's kind of standard. You're not deploying all your systems simultaneously. You often have a sort of ramp up period. So you start with a few systems and then you add more over time as you get them delivered, or as you build them, or as you buy them, or whatever it might be. That will of course affect all these things that we are looking at. It will affect the fleet availability and the readiness, and it will affect what response we can get from the logistics support organization and so on. Another thing that we can do is that we can transfer assets in the simulation as well. So we can say that, well, we might start with a certain set of systems. Here there are 3 helicopters here, 2 and 1. It might be that at some point in time we're actually operating with all of them over here. So we can move things around, but not only the systems. We can move more systems if we want to. We can also move, as you see, you can add resources. We can move resources as well. We can also move around the stock over time if it's that we think that we're moving. But maybe more probable is that we move in additional spares over time as well. So we can move things between stations, as we showed here, or units. And we can also move things from the outside, so we can take things into the model at a later point in time. We can also, as I said, move between, but we can also move to the outside, meaning that we are sort of decommissioning some of the systems, so we are phasing out certain systems and so on. Yeah, so here's an example on just how we did that. And move on. Next thing is what's called time-dependent values. So during the time period or the scenario that we're looking at, some of the parameters will or might change. And such a change can happen at any point in time. So, for example, the mean value for failure rates can increase or decrease at certain points. The duration of performing certain tasks might increase or decrease, or can also be given a distribution. I haven't talked about this, but it's for the simulation, it's actually possible to also define other distributions, not just a deterministic number. Also, for example, reorder lead times. You know that when we are when there's something that we cannot repair, we need to reorder a new one. So the lead time might increase or decrease. It can also be given distributions. And the distributions, while talking about it, they can be used for random draw during simulation. And we can have either integer distributions, so for example, the number of missions that occurs during a certain time period, but it can also be time distributions. So for example, those are more continuous distributions. So used for the length of a maintenance task, or as I said, the lead times or delay times and so on. Okay, take a look at some examples of this in OPUS Suite. So since we are talking about time dependencies, of course we need to be in the world of simulation because it's not steady state when we change things over time. So I think I'm going to start to show you I built a little bit more realistic case as well, not just a single simple engine system that we were looking at before, but here I've built a more complete helicopter. So it's not just the engine system, it has a landing gear system, flight control system, environmental control system, fuel system, and a communication system. So it has 6 different subsystems here, as you saw, and quite many items in each of them, and with structures and etc. We also built up a little bit more large-scale organization with 4 operational bases. In total, there are 20 helicopters in use here, and of course, there's operational profiles and so on, and all that things. So, see, I don't remember. We are looking at a simulation period on that's 3 years instead, I think. Okay, and of course, we've done some kind of spare parts optimization and connected it with an allocation, meaning that we do have a set of spare parts and so on. Okay, and we are aggregating the results per week as well. So run this simulation. As I said, fairly big model, but with you see the replication runs pretty fast anyway. So not the problem that I got when I just put in 1 hour. Here are the results. We can look at, this is what we were looking at before, but here's the total mission results. We can look at as well the system results, the system state. I've removed that percentage. You see we have over 20 helicopters, okay, 20 helicopters. Quite many of them are unavailable here due to different tasks, etc. But what I wanted to show you is what happens when we introduce more additional systems. So I have this other file where we have the concept of transfers. So transfers has its own table category here, and I'm using the system transfers here. And you see that what I do is that I take something from the outside, so it means that we're moving in 2 additional aircrafts to this squadron V1 here, and then 2 to the squadron 1 with 2 over here. So 2 additional helicopters after 2 years, I think that is. Okay, so if we run that case, again, 100 replications. And what happens now is that we see that the number of systems here after this point in time here, after 2 years, you see that it pops up from 20 to 24, so we get more systems. And yeah, so that's what happens. We transfer in more systems here, and we can see that in the results as well. And if we would compare the mission results here between two cases, we will, of course, when we introduce more systems, we can also produce more hours. So we actually produce some more of the planned system time here because we have additional systems. So that's a way of modeling how you can ramp up things. It's actually possible in Opus 10 as well when we do the spare part, the optimization part. It's possible to do something called phases. So you can build up a sequence of phases where we assume that each of the phase is steady state, but it helps us when we have a ramp up scenarios. Maybe let's say we have a scenario where we have a 3-year period where we are operating with 10 helicopters, and then we have a 2-year period where we operate with 5 helicopters, and then we have another 5 years where we have 10 helicopters, for example. Then you can build that up as 3 different phases, and you will get 3 separate CE curves from the optimization as well. So that's another way of handling a ramp up scenario. So that was the I'm going to read my notes here. Now we have a little Swedish lesson here if you want to read this. Okay, I'll move that one. I want to show you also the other one with the time dependencies. We have just closing some files here to just keep the first alternative, sort of the baseline here, the helicopter. And I also have a file where I've added some time-dependent values. Okay, so how does this work? Now let's look at you remember the failure rate table. So here in the simulation, we can, of course, we have the expected value on the failure rate in this column right here. But there's also a column here that says FRTT. So it's the failure rate time-dependent value identifier. And whenever you're insecure of what these different columns mean, I just remind you, we have this context sensitive help. I click that one, drag it to this column. Now I'll click this one, and then I go like this and click. I get the documentation, the help here. So this explains what it is. I can read more about these values and distributions and so on, and click around here to get all the information I needed. Okay. So what it did was here in this case was that we said that okay, there are a few items here that are quite have a really high failure rate. So it's 1600, 1400. There are a few more in the see here 1400. Oops. 1300 for this one, and so on. So what I did was that, okay, so for it's like 10 items or something, 10 items, I think. I created what I call a distribution curve. Instead of having a fixed value on the failure rate over the entire simulation, I wanted to evaluate how the total results will be if the failure rate changes over time, like this. So then I can show you another thing that's pretty cool here. If I click this identifier here, this distribution, there is an arrow here which says go to definition. So then I can click that one and I come to the definition of this time-dependent value. So, but that doesn't say too much. So it's just a definition table. So then I can click the other one here, which is go to reference. So with references, I get up a list of all the rows and column and rows in the entire model where this identifier is used. And this, of course, is not just for time-dependent values, it's for any identifiers in the entire model. But it's also a good way, especially when you're sort of learning how to use the tools, how the different columns are related to each other and so on. So it's, I think it's kind of nice to go to definition and go to reference. Anyway, this one is referenced in the failure rate table. That's where we were before, but it's also here in the time-dependent value data table. That's a long name, but tick that one and hit OK. I'll come there. So this is the time-dependent value data table. So what I did here was to create 3 different levels of the failure rate. And this is, it's not uncommon that people say that, when you're discussing item reliability, to say that in sort of the first year when we are, or in the beginning, it's a quite high tendency of failure of this component. But then it matures, so after a while it works better, it's trimmed into the system, so the failure rate is much lower. And then at the end, it starts getting old, okay? And when it's old, the failure rate is higher. So I did a simple distribution here with a 3-point distribution. So during the first year, between 0 and 1 here, the value on the failure rate is 2,500. During the second year, from 1 to 2, the failure rate is 100. So year 1 to 2. And then the last year, from 2 to 3, the failure rate is quite high, so it's 3,000. Now the question is, how will this affect all my mission performance, etc.? Okay, and also I could apply this to, as you saw before, to maybe 7 or 8 of the most failure-prone items. So we have this, and then of course I want to compare that to the original case with the original failure rates. So we run the simulation for this one, and we'll compare it to the other one. And of course, I don't know which one is better, but it turns out here that with this called bathtub curve, it starts high, goes down, and then it goes up again at the end of the lifetime. So here we can compare those 2 approaches, and here we're again looking at the total system time. And if we do it in percentage, it's the same, but you see that it goes up a little bit actually with these assumptions. But then, of course, it's easier as nothing to go back here and say, well, maybe I was a little bit harsh here, and I want to say that it's 1,200 failure rate for the first year, and it's 1,500 for the last year instead. Maybe I want to say it with a different name. Call it just the dependent values 2. And then I run the simulation again, and I will get a third result. Right now I've run 3 different cases, so I'll get a third one, and then we see how this result plays out. Now it turns out with that kind of reliability, or this curve, we can actually increase the number of system time a little bit from, you see, from 72.3 to 72.9. So then it's actually better. So this kind of sort of sensitivity analysis, or whatever we should call them, or what if scenarios, is extremely powerful and also easy to do once the model is in place. Because I have the model, but I only have to change a few values to be able to do this kind of analysis. Maybe, what do you think, Jan? Is it a good time to go for lunch? So I don't want you to miss lunch. Okay, you want to say something?